We've done a few examples of proof by contradiction now, and hopefully you understand how it works and why it works, and are a bit more comfortable with the idea. Because in that case, we're ready to do two really very famous proofs which rely on proof by contradiction. And these both come to us from ancient world, but are still extremely important results in mathematics. So the first result concerns the irrationality of root 2. So this is a theorem due to Hippasus around 500 BC, but the written record isn't so good, so we don't actually know too many details about the context in which it was done, and really we don't have good proof that it was actually Hippasus, but this is typically who it is ascribed to. And this is the theorem that the real number root 2 is not expressible as a rational number. And this is really one of the most famous results in mathematics, because the existence of root 2 as a real quantity that you can find in the real world comes to us quite directly from Pythagoras' theorem. Once you have Pythagoras' theorem, it's quite natural to build a triangle with unit lengths 1 and 1 and realize the hypotenuse must have length root 2. The square of its length must be 2. And the first proof that this quantity here, which you can find in the real world, can't be expressed as a rational number, was and is still, to an extent, a big deal. It's the first proof that there are real quantities that are not expressible as rationals. And this was really quite shocking to mathematicians at the time. And there's some stories, which I'm not entirely sure how true they are, that Hippasus was either exiled from his group of mathematicians and philosophers, or that they actually drowned him for his proof, which is a somewhat extreme reaction. Now, in order to make this proof work, we need the result that if n is a natural number, or indeed an integer, then n is even if and only if n squared is even. So, notice, here's some scratch work. So, we'll do this by proof by contradiction, so that means that we can write root 2 as a divided by b, with a and b and z, and of course b is not 0. Okay, so that is, we're going to assume that root 2 is rational and reach a contradiction. Or we can rearrange this to get a is root 2 times b, and we can get rid of the square root just by squaring both sides to get a squared is 2b squared. Now the right hand side here is an even number, which means that a squared must be an even number, and by the little result that we had at the bottom of the slide previously, this means that a is an even number, and so we can write a as 2 times c. But if we substitute that back into here, that's enough to tell us that 2b squared is 4c squared, and so b squared is 2c squared, and that's enough to tell us, hey, b squared is even, and so b is even. And so now a and b are both divisible by 2. But if we think about this, this might be the hint of a contradiction, because back up here, if we can write root 2 as a rational number and we discover that a and b have a common factor of 2, we can just divide out by that. And indeed, any time we have a rational number, we can always ensure that the numerator and denominator have no common factors just by dividing out by them. So we can insist that if we can write 2 as a rational number, we can do it with GCD of a and b equal to 1. That is, they have no common factors, because if they had them, we could just divide them out. Now, with that extra condition here, we can still run this same scratch work, do this same work, to find that a has to be even and b has to be even, and that's a contradiction because it contradicts our assumption that they have GCD 1. And that's how we drive the proof. So here is this proof, which is, as I said, an extremely important and really, really famous proof that there exists a real quantity that is not rational. So assume to the contrary that root 2 is an integer, which means we can write root 2 as a divided by b with b 0, b not 0, and the GCD of a and b equal to 1, as they have no common factors. And so then we can do the algebra we did before. Since root 2 is a divided by b, we know that a squared is 2b squared, and so a squared is even, which means that a is even, and so we can write a as 2 times c for some integer c. Well, since a squared is 2b squared, and a is 2c, we can jiggle this around to get 4c squared is 2b squared, so b is 2c squared, which tells us b squared is even, and so b is even. And so we have a is even and b is even, which is a contradiction because we assumed at the beginning that their GCD was 1, and so we can't have GCD 1 and GCD at least 2. That's a contradiction. And so the only way this can work is if back here this was false, and so root 2 really is an irrational number. And so this is an extremely famous and important proof in mathematics, and one that's now accessible to us in this course because we've done all this work earlier in the term. Okay, so let's go on to prove another important result, namely that there are an infinite number of prime numbers. So this was a result due to Euclid around 300 BC, that there's an infinite number of primes. Now we'll prove this by contradiction, but along the way we need a particular result, which I think we have seen in this course, or maybe it was an exercise in one of our classes, namely that any natural number n, if n is bigger than 2, then n is divisible by a prime. So if n is bigger than 2, then it has a prime factor. Okay, now we're not actually leveraging uniqueness of prime factorization. All we need is that any natural number bigger than 2 is divisible by a prime. Okay, now that proof is actually reasonably easy by strong induction. So we can look at the base case here. Since 2 is prime and 2 divides 2, the result holds when n equals 2. The inductive step, well, let's assume that the result holds for all integers up to k. And then, well, k plus 1 is prime, or not. If it is prime, then since k plus 1 divides k plus 1, we've discovered that k plus 1 is divisible by a prime. On the other hand, if k plus 1 is not prime, then we can write as a product a times b, where a and b are both integers bigger than or equal to 2. But by assumption, that means they're both in this pile and so have prime divisors themselves. So we can write a as a prime times c and b is a prime times d. And so k plus 1 is 2 primes times c d. And of course, c and d might be both 1. But it's enough to tell us that k plus 1 has a prime factor. And so this result holds and follows by strong induction. So this is a fairly standard strong induction style of proof. Now that we're armed by that, we can actually go ahead and prove that there are an infinite number of primes. So assume, to the contrary, that there is a finite list of primes that stops at some point, and we can find them all, because it's finite. We could in principle find them, and we can write them down, p1 up to pn. So it's a set of all the primes, and it's finite. Okay? Because we're assuming, to the contrary, this result isn't true. So use this list to compute the number capital N, which we'll call, if my pen will operate here, which will write capital N as the product of all of those primes. Since this is a finite list of finite numbers, this is itself a natural number. And then let's think about that thing plus 1. Well, that thing plus 1 is either prime or not. If it is prime, then we've found a number that's bigger than everything in this list, because it's a product of all of them, and it's prime. So we've found a new prime that isn't in our list. But this was supposed to be the list of all the primes. Well, then we shouldn't have another one. And so that's a contradiction. That shouldn't happen. On the other hand, say, right, okay, well, if n plus 1 is not prime, then it must be divisible by a prime, by the theorem we had just on the previous slide. Well, that means it has one of these primes as a divisor. Let's call it pk. Well, we know by construction that pk divides n, because it's just the product of all of those primes, and it divides n plus 1. So we can write, well, we can just take the difference between these things. 1 is n plus 1 minus n. We know n plus 1 is pk times some number b. And we know n is pk times some number a, because of these two divisibility results. But that means we can say that 1 is pk times b minus a. But this tells us that pk divides 1. And that's a contradiction, because pk is some prime, and all the primes are bigger than or equal to 2. And consequently, with the aid of that bang outside, which you may or may not have heard, this tells us that pk has got to be equal to 1, because that's the only numbers that divide 1. And so that's a contradiction. And consequently, this list cannot be finite. So, that is, there's an infinite number of primes. And I'm going to stop there.